I'm recording, and then after that, I think you guys can come over for the slides. I'm trying to create a YouTube link so that I can always upload them there for you to watch. But I was having challenges this morning, but I will try to make sure that uh, I create the link so that I upload it there and you people will find it easy to watch.
Okay, sir, that's good.
So we continue with Bayesian inference, and we are going to look at how we do that under normal distribution. So here we assume that the variance is known. So what is unknown is the mean. So we consider a model with only one unknown parameter. We shall look at situations where we will consider models with more than one parameter. So let us suppose that we have sample data which has a normal distribution. So if the sample data points xi is normally distributed with mean, and then with mean, and then variance sigma square. And we are saying that I takes values from 1 up to n, indicating number of observations. So we assume that the variance is known, and we assume a prior distribution for the mean. So we say that the data distribution is normally distributed with mean, and then variance sigma square. Now the prior distribution for the mean is going to, so we are assuming that the prior distribution of the parameters also have a normal distribution. But this time we are going to indicate the mean for the prior distribution as mean subscript naught. And then we indicate the variance of the prior distribution as sigma square subscript naught. Now, we wish to construct the posterior distribution for the parameters. So you can see that we are having P, that is the probability of the parameter mean, given the data values, which is X. Now, we know the data likelihood, which is this, and we say it has a normal distribution. And then we have the mean distribution to also have the normal distribution. What we are looking for is the posterior, which is here. Now, the posterior, we have stated in our previous lectures that the posterior distribution of the parameters is equal to the product of the distribution of the data likelihood and that of the prior distribution for the parameters. So if we are saying that the data has a normal distribution and the prior also has a normal distribution, then we multiply the two together to get our posterior distribution, and that is what we are going to do here. Now we are saying that the prior distribution, so we are saying probability of the mean, that is the prior distribution for the parameter mean, is equals to 1 over, or whichever way you want to say it, 1 over square root of 2 pi sigma naught square exponent of 1 over 2, open bracket, mean minus the mean. So this is the mean for the data minus the mean for the prior distribution, all squared. Divide that by the sigma square for the, or that is the variance for the prior distribution. And then let's look at the data distribution. So we are saying the probability of the data given the parameter is equals to 1 over square root of 2 pi sigma square. Exponent negative 1 over 2, open bracket, xi minus mu, all square divided by the sigma square. And this is the data likelihood. Now we have the likelihood function for the two. This is for the prior, and this is for the data. So we have to multiply these two functions together. And in order to do that, so we are going to have posterior distribution for the parameter given the data x. This is equals to the prior distribution for the parameter mean multiply that by the probability of the data given the mean. That is the likelihood function. And that gives us our posterior. So take this prior distribution and multiply that by the likelihood distribution. And this will give you the expression that we have here. This part is the prior distribution. Then we multiply that by the data likelihood here. So what is left is algebra. So if you multiply these two, so what that simply means is that, remember, this is a likelihood function over different x values. So you are going to have, that is why we have the product here, because you are going to have x1, x2 times x3 times x4 in that order. So you get the likelihood function. You have done this under estimation. I shouldn't be worrying myself explaining this to you again. You have done that under estimation. So finding the likelihood function, you know what you are going to get here. Then what you have to do is to expand the brackets here. You know, this is an exponent, and this one is also an exponent. So you can just ignore this and keep them constant, because these are constants and has nothing to do with x. Now you are only having the exponent part here and then the exponent part here. So if you multiply this one by this one, so what that means is that you are going to have exponent of this guy here plus this guy here. So you expand this and then you expand this one also. Then you group like terms. How do you group like terms? What are you looking for? Remember, our interest is on the mean. So where we have mean square, we group those terms. And then these are where we have mean square. So we have mean square, open bracket, 1 over sigma square, that is the variance of the prior distribution, plus n over variance of the data. Now, plus the mean, multiply that by mean of the prior distribution, divide by that of the variance of the prior distribution, plus summation of the data points, divide by the variance of the data. Any other thing that remains becomes a constant because it has nothing to do with the mean. Now, this is what we have. How do we find the mean and the variance after we are able to take the product or to simplify the product into this form? To do that,
Sir,
yes.
Please, where did the n come from? From the equation you just left.
Go and work. You know where the n is coming from. Go and work. You know where the n is coming from. If you take product of this, what are you going to get for the constant? If you sum a constant over and over and over, what do you get?
Okay, sir.
Go and solve it out. You have done this under estimation. Don't waste my time here.
It becomes n.
So now let's move on. So for a normal distribution with response y, the mean theta, and then the variance phi. Now, here our y is the value of interest in this case. So here we are saying that the y has a distribution which is normal, and then we have 1 over square root of 2 pi, that is the variance, exponent of 1 over 2, or theta squared. Yeah. Okay. One over square root of 2 pi. That is Please, if you want to talk, you draw my attention. You don't just start talking. If you do that, I will remove you because you are causing noise in the background. That affects everyone. Please, if you want to say something, draw my attention, then we'll allow you, to talk. We'll give you the floor, but you don't just start talking to disrupt our lectures. I'll mute you, then you unmute yourself. Why do you do that? So we are saying that for the normal distribution with the response y, with mean theta and variance phi, the distribution for y is represented as this, which is just the normal distribution. Now ignore the square root part and focus only on the exponent. That's why we say this y is approximately equals to this guy here. So if you expand this, this is exactly what you are going to get. Now, once you get this part, what you have to do now, relate what you have here with what you have in the previous slide. So if you check in the previous slide, look at the first part here. Just look at this first part. Where do you have y squared? So you have y squared here. So you go back to the previous equation and check where you have mu squared. So if you go back, where you have the mu square is here. So you are going to equate. So in the other equation, you have 1 over minus 1 over 2, and then you also have y squared. And then after that y square, you have this guy here. So what that simply means is that the phi up to the power minus 1, which is just the same as 1 over phi, is equals to 1 over sigma squared naught plus n over sigma squared. So the phi up to the raised to the power minus 1 is equals to 1 over the variance of the prior distribution plus n over the variance of the data. That is the variance of your data. Now compare this aspect also to the data y distribution in the next slide here. So you can see you have y. So in that equation there, your y is the mean. So what is remaining is this guy, theta over phi. So theta over phi, compare that to what you have in the previous slide. So if you do that, you have the y here. So this mu is your y. So what is remaining here is equals to the theta over the phi. So that means this theta over phi here is equals to the mean of the prior distribution divided by the variance of the prior distribution plus summation of the data points divided by that of the variance of the data. So this, what is inside here is equals to the theta over phi. Now solve that out. So if you pick that out, we are saying that 1 over phi, remember 1 over phi is the same thing as phi to the power negative 1, which is just the inverse of phi. Now that is equals to 1 over the variance of the prior distribution plus the number of data points divided by the variance of the data and the mean. Remember we said mean over phi is equals to this component here. So if that is so, then that can equally be written as, because it's mean over phi, so we can just multiply the phi here. So it's just going to be the theta equals to the phi, multiply that by the mean of the prior distribution, divided by that of the variance of the prior distribution, plus the mean, divide that by sigma square over n. This is another way to express it, whichever way is all fine. So here we have the variance of our of our posterior distribution, and then we also have the mean of the posterior distribution. So if I give you the prior values and also the data values, you should be able to find the posterior mean and also the posterior variance. Now,
Okay, sir.
yes.
So our interest is only to determine the posterior of the data. Is that not it?
Yes.
Okay. And I'm also seeing cons plus cons. What's the meaning of that, please?
Which one?
In one of the previous slides, this one. No.
Yeah, so I said that you are grouping like terms. Whatever is
Okay.
remaining, which is not in terms of the mean, is a constant.
Okay.
So you
Okay.
group the mean that are the variable that are having mean square. You
Okay.
group those that are just having the mean. Whatever
Okay.
remaining and that is not in terms of the mean is constant. It's just
Okay.
like you
Okay, sir.
have x squared plus 3x plus 2. The 2 is constant. It
Oh,
doesn't depend on the variable x.
well
Here,
understood,
our
sir.
variable
Thank
of
you.
interest is the mean.
Okay.
So any other thing that is not in terms of the mean is a constant. And that is what we've
Okay.
written here.
Okay, sir. Thank you.
Is that okay?
Yes, sir.
So now let's move on. So we know our mean and variance of the posterior distribution. And this is just more simplification of that. Let's see how we apply this. Now let's consider a data on girls' height. 10 girls, age 18, had both their height and weight measured. So 10 girls and their ages were 18. Their heights values are as follows. You have them here. Now, we will assume that the variance of the data, the population is known to be 50. So two individuals give the following prior distribution for their mean height. So the individual one says okay, we are dealing with only girls. So her age is 165, and then the variance is 4. The second person says her age is 100, her height is 170, and the variance is 9. Now, with this information, and using now we have recorded their data, how do we update this prior information? So that means we need to compute the posterior distribution for the mean and also the posterior distribution for the variance. So now let's see how we update that. So from the information that has been given, let's consider the first person. So with the first person, the prior distribution, that is the mean naught, is equals to 165. The variance of the prior is 4. And then the data mean, you can just go there, compute the data mean, you will get 165.52. And then the variance from the population, which is this one. And then we have that of the points, the data points, which is 10. So the posterior distribution of the mean of the data set is normally distributed with the mean, that is the mean 1, because we are just using mean 1 to indicate that, theta 1 to indicate that we are dealing with the first individual, and then variance or the phi 1 to indicate that we are dealing with the first individual. So we know that the variance is defined as 1 over the variance of the prior distribution plus the number of data points divided by the variance of the data. So here, if we take 1 over that plus 10 over 50, and that we are going to get 2.22. So the mean, the variance of this individual is 2.22. Then let's look at the mean. The mean is equals to the variance, multiply that by the mean of the prior, divided by that of the variance of the prior, equals to the mean of, or the summation of the data volumes divided by that of the variance of the data here. And if you do these computations, you are going to get 165.23, representing the mean of the first individual. So you have updated the information. So you have used the information that the person has given, and then you use the data information to update that person's information. And this is what you actually have. So the variance is actually this, and then the mean is this. So you can consider the second individual, and then you do the same thing. So the second individual values are here. So you can consider that. So these are the prior mean, this is the prior variance. So you go and substitute them here and then see what you are going to get.
So, sir, please,
Yes.
in this typical example, we can draw an inference that, please, if you can go to the slide. We can draw inference from the fact that actually the mean height of the girls is 165.23.
Yeah.
Is that it?
Yeah.
Okay.
So this
Okay.
person gave you her prior height to be 165, and that the variance is 4. Then you went ahead and then collect your data, and then realize that the age, the mean height is 165.52, and the variance is 50 on
Okay.
10 data points. And now you want to update the prior information here. And after updating the prior information, you realize that the variance is actually 2.22. And then the mean is 165.23. So you can see in terms of the mean, they are almost the same. In terms of the mean,
Yes.
what the person gave as the prior mean is almost the same as the posterior mean here. So what is little different is the variance. So the variance is a little bit lower in the posterior distribution compared to the variance in that of the prior distribution. Then you can also look at the distribution curve for the prior, the data itself, and then the posterior distribution. And that is what we have plotted here. So you can see the mean age is in the middle here. So the posterior is having the red. Those of you who will do the course in the second semester, we shall use computer to simulate the parameters, and then we shall plot the posterior, the prior, and the data likelihood, and see how they are going to behave. So we have our prior, which is the blue, and there we were saying that the variance is 4, and then the data likelihood, which is green, the variance is the data likelihood, the variance, I think when we computed, what was it, 50. And then we consider the posterior, and the posterior is the red one. So you can see when you've done descriptive statistics, right?
Yes, sir.
So how, given these curves, how do you know which one has higher variance compared to the other? What will you use to know
How
that? Just
how wide they
how
are?
will you know that? How will you tell which one has higher variance and which one has lower variance?
How wide the curves are?
Come again.
How wide the curves are? So the
How
wider the
wide the
curves, the higher
okay,
the variance.
that's fine. So we look at the thickness or the convexity of the density curve or the density plot, and then we'll be able to tell whether there is high variability here and low variability here. So if you look at the blue, which is the prior, you can see that there is kind of higher variance compared to if you look at the red line or the brown curve. And then also you look at the green curve and you can see there is higher variability also as well. So yes, you look at the thickness or the convexity of the plot to tell where there is higher variability. Yeah. So in effect, the variability that the person has given is actually lower than what the person has given. But in terms of the mean, we can say that they are the same. Yeah, in terms of the mean, we can say the same because the variance that we have gotten is almost half of the variance of the other one that we have. So variance, lower variance in the posterior compared to what the person was given as a prior distribution or prior value for the mean. Any question? So now we talk a little bit on prior distributions. How do you choose a prior distribution for a parameter? We have certain parameters that we call conjugate priors. So the conjugate priors are such that when you multiply them by the data likelihood, the end or the final result or the product of that is going to give us the same distribution as the data. So if I take a normal prior, that is parameters that are assumed to have prior distribution, and multiply that by data that has normal distribution, then the posterior result is also going to be a normal distribution. When you have such priors, we call them conjugate priors. So for instance, if we have data likelihood to be normal distributed, then the parameter we are interested in is the mean. Then if we use a prior distribution to be normal, then the resulting posterior distribution is also going to be normal. So this prior, we call it conjugate prior. Then under normal distribution, if we use a distribution for the variance, and then that is the precision, which is 1 over the variance. Then we assume that the prior distribution for the precision is gamma. Then we multiply the gamma distribution with that of the precision parameter, where we say it's normally distributed. Then we get a gamma posterior. And what that means, the prior distribution, the posterior distribution is also having gamma distribution, and therefore we have a conjugate prior for gamma. Then under binomial distribution, the conjugate prior is beta. So if we multiply beta distribution of the parameters by the binomial distribution for the data, then the resulting posterior is also beta. Then the Poisson distribution, if we assume gamma distribution for the Poisson, for the parameters in the Poisson distribution, then the resulting posterior is also going to be gamma distribution. So whenever you take a prior distribution and whenever you assume a particular distribution for the prior and then multiply that by the data likelihood, and the end result of the posterior is the same as that of the prior distribution, then such priors are referred to as conjugate priors. Of course, there are other priors which we refer to. Some of them are non-informative. So that is used in a situation where you don't have much information about the study that you are going to undertake. So that means you provide little information about what you are about to do. And we call that non-informative priors. So we often do not have any information, although through Bayesians will argue we always have some prior information. So we will hope to have good agreement between the frequentist approach and the Bayesian approach within a non-informative prior. So there are sometimes we use what we call the diffuse priors or the flat priors, just to indicate that the information that they are adding is not much. So for example, so if, for example, of unknown mean, you don't know the mean, candidate priors are usually the uniform distribution over a large range of a normal distribution with a huge variance, or a normal distribution with a huge variance. And then we have also improper priors. If you take a prior and then you integrate it and then, or you sum the values up and you don't get up one, we call that improper priors. But we can always use them and then check the convergence of our posterior distribution to know whether they are actually converging to one or not. If they don't converge to one, or if you integrate the function and you don't get one, what that simply means is that you are not going to be able to use that improper prior. So this is just an example of a uniform distribution. So you can, if you don't have much information about what you are dealing with, then you can just say that, okay, the parameter have a uniform distribution over a range of values x0 up to x1, and that is all. So this is just example of Gaussian distribution with the same thing as we have done. So this is the data likelihood expressed as that. And then we have, okay, the data likelihood here, then the prior distribution here. So here they are using delta and they are using tau to represent the variance and then the mean for the prior distribution. So the other case, we use mu naught and we use sigma naught. So here delta is used for the mean and then the tau is used for the variance. So tau square is the variance here. So it's just notations, but the same thing. Then you multiply the data likelihood and then the prior together. So the data likelihood is here, then the prior is here. And then you do your arithmetic and then you arrive at the same thing that we had. And you can see the details here. So you can follow that if you don't understand the first one. Yeah, the same thing. Now, let's look at situations. So the first one that we looked at is normal distribution for one data or one parameter of interest. So here we are going to look at binomial distribution. So under binomial distribution, here the data are binary, where it is just yes or no. Now we have a Bernoulli distribution, which is just equals to theta to the power the data values 1 minus the theta 1 minus that. However, if we take the likelihood function over time, then we get kind of a binomial distribution, which is here. The binomial distribution is theta to the power y 1 minus theta n minus 1. You know this already. And we are saying that the y, instead of, we didn't bring the yi anymore, because when we take the product over, we are going to get summation of y. So instead of writing the summation of y, we just represent it by y. That is the bold y without the I in there. So that's why you have them here. And our interest is to find the posterior, because this is the data likelihood. So our interest is to find the probability of the parameter given the data y. What we have here is the probability of y given the parameters, but we are interested in the probability of the parameters given the data, and this is the posterior. How do we define that? So to do that, let's look at the beta distribution first. These things you have done them under estimation, right?
Yes, sir.
Yes. So you know that the beta distribution is given by this, and the mean of the beta distribution is theta over, is alpha over alpha plus beta. This is the mean for that, and under estimation, you should know how to get this guy here. So if you choose different values of alpha and beta, these are the kind of shapes that you are going to get. We shall play with these things, those of you who will be doing this in the next semester. Then this is the same as the beta distribution, just more information on that, but it doesn't change anything. Then the variance of the beta distribution is given as this. So if I multiply the prior distribution, yes. Ask your question.
Please, for the curves, you've not done it in estimation. You ask.
You have not done the curves in estimation.
Yes, sir.
Yeah, for the curves, we are just showing how different values of the parameters will change the distributions curve. That is all that
we are. Please, can you go over it again?
We are just saying that with the curves, we are just showing how different values of the betas and then the alphas will change the curves of the distribution. So you can see that we have chosen different values. Look at the black line. We have chosen alpha to be 2 and then beta to be 4. And we have a kind of curve that has a chi-square distribution. And we decide to choose alpha to be equals to 3 and then the beta to be equals to 3. And then you can see that we are getting a curve that is normally distributed, but then it is very broad. And then we choose different values. So you can see these values. We've just swapped the first ones. Okay, we just swapped the first one. So alpha was 2 on the first case. And then this time, the alpha has changed to 4. And then the beta was 4. And this time, it has changed to 4. So you can see that you have kind of a data that is kind of skewed to the left here. And this one skewed to the right here. So these are the various distribution that you are going to get. So depending on the theta, the alpha and beta values that you choose, you have a certain kind of distribution appearing. So that is the illustration of these figures that we have here. And remember, we said that as you increase your sample size, the probability distribution will converge to the normal distribution. So as the sample size increases, the probability distribution of any distribution will converge to the normal distribution. So that is that there in the case. Then the variance of the beta distribution is alpha times beta, divided by alpha plus beta all squared, open bracket, alpha plus beta plus 1. So if I multiply my prior distribution of the data, of the parameters, and with that of the binomial distribution for the data, then I'm going to get a resulting posterior distribution that is also a binomial distribution. And in that situation, I'll be able to find my beta and find my alpha and substitute them into these equations. That is the mean and the variance. That will give me the posterior mean and then the posterior variance. So the posterior mean is alpha over alpha plus beta. The posterior variance is alpha times beta divided by alpha plus beta all squared, open bracket, alpha plus beta plus 1. That is the variance. So if I know my alpha and my beta, I just substitute them in here and I'll get my variance. And also I substitute them into the mean and then I'll get my mean for the posterior distribution. Now, if you consider the posterior distribution, so here we use.
Hello, sir.
Yes.
Please, as a researcher, can you be asked under any condition
come again
to prove, as a researcher, Can you be asked under any condition to prove how you arrived at the variance,
But that is
the
basic,
mean?
which you have done under estimations. So are you telling me you haven't estimated this under estimations?
But I'm asking, going on. I mean, is this anything normal to be asked?
Come again.
I mean, statistics is a course of graduation where all these basics, probably some of the times you just use machines to manipulate these
Then
parameters.
go straight and ask your question. We have no time.
Yeah, the question is that can you be asked under any condition to prove these things?
So what is your problem proving this if you are asked to prove them? Because you have done them in, I think, second year or third year. So what is your problem proving? Whether you are asked to prove it or not, is that an issue? Just know how to prove it, and that's what. Whether you are asked or not, then it's fine. If you are asked to prove it, if you are not asked, then you ask and move on.
Okay, sir.
Yeah.
Okay.
So if we take the data likelihood, we know the binomial distribution is, I'm just ignoring, binomial distribution is n choose x. You know that. But I'm just ignoring that part because that part is constant. I don't need it. So here, I'm just saying that theta to the power y, open bracket, 1 minus theta, all to the power n minus y. That is the data distribution aspect, and that is that one here. Now, the prior distribution is the beta, and what you have here is the beta distribution. Look at the beta distribution, and then for the parameters, and that of the binomial distribution. You can see that they are almost the same, except that here there is alpha minus 1, here is just y. Then here is beta minus 1, and then here is n minus y. Otherwise, these are just the same. Now, if we multiply these components together, what that means that we have theta multiplying by theta to the power alpha minus 1. This is going to give us theta to the power alpha plus y minus 1. And then what is in the brackets here, multiplied by what is here, then we are going to get 1 minus theta because that is common to here and there. Then we add the exponent, and that is going to be n minus y plus beta minus 1. Now, compare this to the previous beta distribution. So that means all that you have here, okay, compare this to the alpha, to the beta distribution here. Look at the beta distribution here. Look at it. You have theta to the power alpha minus 1. And then when you multiply it under the posterior, you have theta to the power alpha plus y. So in this situation, what is different is just alpha plus y here. So your alpha in this equation here is now equals to what? Alpha minus y. This alpha in the posterior here is this equals to alpha plus y. Now compare the beta. The beta in the gamma in the beta distribution is beta minus 1. But now we have n minus y plus beta. So what that means, the beta that you have there is just n minus y plus beta. So what that means is that your beta distribution or the posterior distribution has a beta distribution, and the alpha now is going to be alpha plus y, and then the beta now is going to be beta plus n minus y. And this, so that means your posterior mean for the beta is alpha plus y, and then the posterior for the beta is beta plus n minus y. So we know the mean for the posterior, or the alpha for the posterior, and then that of the beta for the posterior. We can do the same for the gamma distribution, but our time is up. So we have to stop here, and then we continue the lectures next week. So if you guys have questions, yeah, you can go ahead and ask.
Yeah, hello, sir.
Yes.
Please, the videos for when are we going to see them?
You come for the videos are too large. I can't load them. I can't upload them in the
Okay.
WhatsApp group.
All right, I would come for it. I'll come for it.
I tried creating a YouTube channel to upload them, and it's telling me that the file size is too large. I don't know, maybe whether
All right, I would bring a pen drive and come for them later.
so you can come for them in a flash drive so that you can share with the class.
All right, no problem.
Otherwise, if I'm successful in uploading them in the YouTube channel, I will send you guys the link so that you can just open on your phone and then we listen to the lecture.
Okay. All right, then that'll be fine too.
So we'll have our face-to-face meeting. Is it Friday or?
I think so.
Yeah, our face-to-face meeting is Friday. So
yeah, on Friday.
Yeah, so we meet on Friday.
All right.
Yes, sir. So I think with the YouTube upload, no,
yeah,
there could be a way to compress it or reduce it.
Find out that way and come and tell me.
Said the
Okay.
face-to-face class is tomorrow rather, not Friday.
It's tomorrow, yeah.
Yes, sir.
Okay, that's fine.
All right.
Sir, our face-to-face meeting is Thursday.
It's Thursday. Yeah.
Yeah, yeah.
Okay, that's fine. So we'll meet tomorrow.
Sir,
Okay. All right. Bye-bye.
Bye.
Sir.
Face-to-face,
Sir.
yes.
Yeah, Ben.
Sir,
No,
can
I
you hear
wasn't
me?
saying anything.
Yes, I can hear you.
Sir, please, the lecture slides you gave us.
Okay.
Many of the things are missing from the lecture slides. So please, if you can read
I don't understand.
them
Or updates.
or update it for us.
I've not changed anything. Everything.
I was following what you were doing with the lecture slides on my phone, but many of the things were missing from the lecture slides.
Just point one. You just said many of the things. Just point one. Example.
Okay, so for instance, the beta binomial model.
Yeah.
For all you were doing, the place was empty.
It's only this one.
The
that
only
I've
thing
just
was
added.
a
Look at
pointed arrow which has
Only
been
this one.
written needed prior.
Can you see this? This is the only thing I've added in the slides. And I did that because of this. You can see here, the variance cannot show up. I just realized that this morning.
So even,
Come again.
so but even the first slides
The first,
concerning the posterior of the normal distribution, the posterior for the normal distribution didn't show on the slides here.
you mean
The
here?
calculation, all I saw
You
on the
mean
slide,
here?
so we have,
You don't have this one in your slides.
and that was all. The posterior for normal distribution.
You don't have this in your slides.
Yeah. Yes.
You don't have
Yeah,
this
we
in your
have.
slides.
Yes, sir.
Can you just send
The
that
only
to
thing
my
over there is
WhatsApp now?
the. Yes, sir.
Just WhatsApp that to my this so that I can confirm because
Okay, sir.
it's the same slides I'm using.
Okay, sir. Thank you, sir.
Just send that now. I want to open and check before you go.
Okay.
No, I know. I mean, let's see.
Sir, please, it has been sent.
To the group or where?
Yeah, the Bayesian Stat 403 group.
I've not seen it. Someone just joined now, but I've not seen the upload. Under the Bayesian, you can see, okay, it has come.
Okay.
Who is that 18 in the class? -5.
What is happening?
So Ben, where are you
Right.
saying that you don't have it? Look at it here.
No,
Huh?
no, sir, please, it's Malta. Malta says it doesn't.
Come again.
Malta, talk to sir.
Come again.
Joshua.
Yeah,
Ah,
Just
you come
says the
again.
one
Then to be
complaining,
from
not
the,
me, sir.
the app I'm using to open it.
Come again.
I said, then it to be from the app I'm using. Because that part is not
So
showing.
if you have problem with your lecture slides, cross with the other colleagues and find out whether you have wrong slides or not. You don't delay our class for nothing. Because I don't think that is what your other people have. Check with them. Are they all having the same problem? Is all the class having the same problem? They can't see that part. Hello?